that would be, so basically I21 is minus I12, right? Since we are going for, we're just assuming directions, so this would be plus V2 minus V3. So just I'm just deriving it again so that just refreshes your memory. I'm sorry. Y23, right? So if we rearrange this, we would get Y12 V1 plus Y22 V2 plus Y23 V3. So one thing that you will see is that Y21, this is actually Y21, right? Y21 and Y12 are the same, right? So finally, if we write for all three buses, we will get Y11, Y12, Y13, Y21, Y22, Y23, and Y31, Y32, and Y33, right? So if you remember what I said in the last class, okay, yeah, YII is actually the self-admittance, and that is actually the sum of all elements connected at node I, right? Whatever lines are connected or whatever components are connected to node I, we take the sum of it, and Yij is actually the minus negative of the admittance of the line between node I and node J. Is that clear? Right? Yeah. Right. So one thing that you have to see over here is that what does y, suppose y11, right? It is actually, suppose what is y11? It is the sum of y12 plus y13 plus y14. I am assuming that it is an n-bus system, right? Plus etc. plus y1n. And what is y? Y is basically the admittance. Sorry, y12 small. What is small y? Small y is the actual admittance of the line between node. Suppose this is I and this is J, right? And the impedance is Zij, where Zij is the actual resistance Rij plus J X I J, right? So what would be Yij? 1 by Zij. Okay, so usually if you are assuming that the resistance is less, this would be Jxij, right? And that would be minus J Bij. right? And this is, if it is basically a inductive component, it would be minus j, and if it is a capacitive component, it would be plus j. Is that clear or is that confusing? So the admittance y for a inductive element would be negative, and for a capacitive element would be positive. All right, okay, right. Okay. Say suppose let's look at this. This should come as okay. When we are talking about resistance in terms of ohms, this is 3 ohms, right? This would be J 3 ohms, and this would be minus J 3 ohms. All right. So when we take the admittance Y for the resistance, it would be 1 by 3 mho. For the inductor, it would be minus J 1 by 3 mho. And for the capacitor, the Y would be J 1 by 3 mho. So basically, if the admittance is plus J, positive J, then represents it represents a capacitor, and if the admittance is negative J, then it is actually an inductor. So sometimes in questions, what they will do is that they will not actually say if it is the reactance or the admittance, but they will give you the network diagram, and they will mark plus J3 or minus J3. So based on the sign, you should be able to identify what that is, right? So I'll just write down a table. If you guys are making notes, I will recommend noting this down. So the reactance, then admittance, impedance, right? So if it is an inductor, it's inductor. This would be negative and this would be positive. For capacitive, this would be positive, this would be negative. Is it better now? Okay, good. So, okay. So now, okay, so what happens is that, so predominantly our power system network is inductive in nature or reactive in nature, right? Inductive in nature. Uh, is that clear or is that confusing? That if I say that our power system network is predominantly inductive in nature, is that a statement that you would support, or is that a statement that is confusing for you? I think you guys are quiet. I just need some response from you guys. All right, this okay. So one person told me that they need clarification, and I will make the clarification. So the idea is that let me go back here. Okay, the idea is that what are the major components in our power system, right? One is generator, right? And what is the what is the nature of generation? It actually is a coil, and that is inductor, right? Then what do we have? We have transformers, and transformers are again two coils, right? And that is also inductor, right? Then we have transmission line. Line is based on the line length. It is having both inductive as well as capacitive, but the capacitive effect is actually very weak, right? It is small. In some cases it is not negligible, but in most of the cases it can be neglected. So it is inductive in nature. So when it comes to a transmission line setup, right? So we are looking at a transmission line setup over here. Yeah, sorry, we are looking at a transmission line setup over here. So it is predominantly, if you look at the total reactance, it is predominantly inductive in nature. So when we are looking at Y12, we are talking about the element between node 1 and node 2, which is usually a combination of a transformer, a transmission line, and a transformer, or sometimes it is usually just a transmission line. Unless and until we are having an HVDC line, or we are actually adding physical capacitance in the form of series compensation, it is predominantly, or by general nature, it is inductive in nature. So does that make sense now for the people who it didn't make sense earlier? Okay, cool. Right. So that's why we say that since it is a summation of all the components, usually we get the diagonal elements as very high value of minus 0 terms, right? So this is like things to remember when you're looking at the Y-bus matrix. Just to see if you remember this when you're analyzing problems, it will make sense to you very quickly. And what is this? This would be positive because it is negative of that element. So this would be J something like J2 or J10 or something like that, right? Okay. And suppose there is no transmission line between 2 points, then the corresponding element would be 0. Okay. So if you're looking at N bus, you see that Y bus is an square matrix N cross N, and one more interesting fact is that Y bus is always symmetric, right? Y bus will be always symmetric. Okay. Okay. Now the question of, so right till now we were going with the assumption that okay fine, there is only resistance and reactance in the transmission line. But now if you are having a medium to medium transmission line or a long transmission line, then the capacitive effect between the line and the ground, earth, the actual earth, will come into picture, right? So what we have to do is that we also have to take into account that capacity effect. Basically, if you think about it, what is happening? Line is one plate of the capacitor, right? Line is one plate of the capacitor, and earth is, this is our ground. This is another plate of the capacitor, right? And what is the other thing that you need for a capacitor? There should be a dielectric in between them. And what is the dielectric over here? Air, right? So basically what happens is that when you're having a high voltage transmission line uh, over a long distance, this capacitive action cannot be ignored, right? So what we do is that we call it as line charging admittance, and we add a capacitor to this model. So have you guys learned about uh, T and pi representation in networks? If you are having three elements, you can either represent it as T or you can represent it as pi. Are you familiar with this concept? Right. So everybody is familiar with T and pi. Okay. So tell me. Okay. So tell me when we are so right now what we have is we have three elements, and like this we have, so basically there is a series element and there is a shunt element, right? So this is right now a T model, right? So when we are talking about power system, or when we are looking at this model, we should we go for a T model or a pi model? So if we are going to represent a transmission line, which should we go for? All right. Okay. Okay. So we have a mixer bag over here, right? Uh, one thing though, Sakura, right? Sakura, are you able to see these codes that I'm putting up? Okay. So actually, if you're looking at a network representation, uh, what will happen is that suppose if you are going for a T model, right? If you're going for a T model, it would be, yeah. If you are having some issue with this, probably we'll have to talk to um, Dinesh sir to figure this out for. Not figure out, that's okay. No, just wanted to see that you don't have any technical difficulties, right? Yes, okay, that's fine. So if you're looking for a T model, what we'll do is that we'll split the series elements into two, and we will put the end element in the middle, right? What does this do? So this is node 1, node 2, this would be a new node 3, right? What this is R by 2, X by 2, R by 2, and X by 2, right? And this is Y, right? And if you are looking for a shunt or pi representation, right? So if you see, both representations are we can work with both representations equally. But the problem is that here, if you see, for the transmission line, effectively, suppose you are having a 100 bus system, right? And between these 100 buses, there are 100 lines. Okay. And when we are trying to, we are going with a node based, or when we are looking at a node based approach, so we will have the Y bus as a 100 cross 100 matrix, because 100 nodes, right? Now, but if we are going for a T representation, each transmission line will contribute to a new node. So basically, that would be suddenly based on the number of transmission lines, the size of the matrix increases. And when the size of matrix increases, the computational cost and the computational processing required also increases. So for power system, we always prefer to go with pi model. Is that clear? Does that make sense? That we will always prefer to go for pi. All right, good. So what we do, so this is called as half shunt line susceptance or half shunt line admittance, right? So basically we have transmission line, and whatever is the capacitance or the capacitive admittance for that line, we divide it into two and add it to the two ends of the node. Now let's look at how this will affect our Y-bus formulation, right? So what happens now? One more current component will be there when we are considering KCL. So it will be I12 plus I1 dash, right? So when we rearrange, we see that we have to add the Y12 dash by 2 to the diagonal element, right? Basically, if there is a shunt at any node, the corresponding admittance gets added to only that node, right? So basically, if we are having a transmission line that actually where we have to consider the capacitance, we'll divide the capacitance by 2 and add it to the diagonal elements of the two nodes, right? So basically, so if you are looking at the 3-bus system, it's basically Y12, Y13 plus half line capacitance of line between 1 and 2 and Y1 and 3. Similarly, if you look at Y22 to be Y21 plus Y23 plus Y21 by 2 plus Y23 dash by 2, right? So basically, for the diagonal element corresponding to 2, we'll add the half shunt capacitance or half shunt admittance to of the lines connected to that node, right? Similarly, for Y33, we will add uh, this and this, right? Make sense? I'm trying to pick up a little bit of pace here, given the feedback that I got from you guys, and you guys are able to pick up fast. If my pacing is becoming a little tough for you, let me know. Okay, right. So now, if you look at this is now what we are going to do is that now we are going to look at a 4-bus system, right? Now, if you look at the 4-bus system over here, you will see that since there is no connection between 1 and node 3 and 1 and node 4, this would be 0, right? And only for the place where there is actually a physical transmission line, we will have a value in the Y bus, right? So let's look at this one. Can you guys draw this down? So just let me know in the comment section once you have taken the drawing down. Are you done? Okay. How about others? Right. Varun and Mahak? Okay, right. Now, can you fill the, okay, this is the Leaning Tower of Pisa, ignore it. Can you fill the Y bus for me? Just in your own notebook, fill the Y bus. I'll give you 2 minutes. Okay, I want you to fill it in terms of small y. Okay, so basically y2 on capital this position. I'll give you an example. This position, second position, right? Second position would be minus y12, right? So once you guys are done, just let me know. Okay, I'll start filling it over here, right? So this would be what we're going to get to 114 and 112. So this would be y12 plus y14 minus, again, the next element would be minus y12. Somehow I have to write down this one today. So there will be y11, y12, 0, y14, 0, and 0, right? Where y11 is equal to y12 plus y14 capital Y12 is minus Y12, capital Y14 is minus Y14. Did you guys, okay, done, good. So did you guys get this so far right? This one, you guys got it right? Right? Okay. Okay, good. And what would be the 2? 2 is between Y12, there is only one element. So it would be capital Y21, capital Y22, and everything else would be 0, right? Where capital Y21 is equal to minus Y22 is equal to Y21, correct? Similarly for, oh, my bad. There is one more connection. It's wrong. I hope you guys will correct me. Guys did not correct me. Now I'm going to intentionally make mistakes just to see if you guys will correct me. 550. Right? Okay. Okay. So Y25 will be minus 525. Okay. This should have written this one properly. So give me a second. Wait, are you guys able to see my screen? I hope, yeah. Okay. So basically this was Y12. Okay, Y12 minus Y12 plus Y14 minus Y12 0 minus Y14 0 and 0. Right? Second one was minus Y12 Y12 plus Y25 0 0 minus Y25 0. Right? Okay, then with node 3 there is only one connection, that is Y36. Right? So node 3 would be 0 0 Y36 0 0 minus Y36, and node 4 is only one connection, that is Y14. Right? y41 and y14 are the same because transmission lines are, if we are considering pi model, it will be symmetric in nature. Even if we are considering p model, it will be symmetric, right? Unless and until, again, there are conditions. We will look at that conditions later, right? Then what about 5? Node 5 is connected between, it is connected to 6 and connected to 2, alright? So 0 minus y52, 0, 0, y25 plus y56 minus y56, right? And this last one is connected to node 3 minus y36, 0 minus y56, y56 plus y36. So this is your y. So did you all get this one? Not y36, is it? There's no connection between 3 and 6. There is connection between 3 and 6, right? Yeah. So you guys all got that solution, right? Good. And just leaving a poll just for my peace of mind. If you got it, just let me know as yes. Varun, okay, good. Thank you. Thanks a lot. Okay, so if you see over here, one thing that you can see as it becomes more and more, this thing is that there are a lot of zeros, right? So if you're looking at power system, there might be 1,000 bus, but any given node probably will be connected to maximum 1 or 2 nodes or 3 nodes at a time maximum, right? So a lot of the other, so since there is no connection to all the buses, a lot of elements of this bus would be 0. So basically, Y bus is actually a sparse matrix. Does that make sense? That Y bus will be a sparse matrix, right? Yes. Okay. I'm assuming it's an yes. Now that we have got all the concepts, we have gotten the concepts of power system. Let me give you this question. I want you to think about everything that we have talked so far about a Y bus, and then approach. So I have not given you all, like I have not given you the exact approach to this kind of problem, but I have given you all the information required to approach this problem, right? I want you to think about this problem and give me the answer. Or let me do something. Let me get rid of this poll and I will create a custom poll so that it's more. Think about it. Don't go for option E immediately. Just think about it and let me know. So for people who are confused, if when they're saying 50% sparse, it means that 50% of the elements are 0. So far I got one response. I'll wait for one more minute. All right. Okay. Good. Good. Okay. Varun. Okay. Cool. Cool. So most of you said that you need help. Okay. Let me go with this. So one thing that you have to assume. Okay. Again, I always am going back to what I keep on saying to you. Ask what are the assumptions. So the assumption over here is that it's an interconnected system. So interconnected system means that there is every transmission line has at least one line, right? So there is no island, like island money. So suppose there are three buses. There is at least one line connection to each, right? So it's not like this, that this bus is islanded, there is no connection, right? So this is like an interconnected system where you can actually have an electrical path between one node to another node, right? So that is the concept of interconnected system. So now so if you have an interconnected system, the diagonal element YII will not be equal to 0, right? Okay. So now what they have said is that they have a 50 bus system. So what will be the size of the number of elements in Y bus is equal to, that will be, right? Is that clear? Now what they're saying is that 50% of it, 50% of it is sparse, right? So oops, okay, my bad. Actually, none of these options would work because the question was 80%, my bad. Again, anyway, so 50% sparse means non-zero elements is, so number of elements is equal to 50 into 50 This is 2500. Actually, there was a typo in when I typed the question. There's actually 80% sparse, right? Let's solve it with 50%. When we're solving it with 80% only, we'll get the option. But let's go with 50%, right? So when you're going with 50%, number of non-zero element would be 0.5, or let me put it as 50 by 100 into 2500. That would be 1250, right? Out of this, 50 are diagonal elements, right? Number of non-zero of diagonal elements would be 1250 minus 50, that would be 1200. So it means that there are 1200 non-zero of diagonal elements, right? So since it is symmetric, uh, two numbers represent same transmission line. So number of transmission line would be uh, answer would be 600. There is a typo in this question. It should have been 80% over here, right? It should have been 80%. But uh, does that make sense? You can try this question now. And let me know what the answer is. So these are also type of questions that you get in GATE where you have fill in the blanks, right? So let me know what the answer is. I'll give you 2 minutes because this is usually a 1 mark question. So you have 2 minutes. Okay. So one answer is 450. Okay. So we have one answer is 450. Okay. So let me see. Right now I'm putting 450. If you have another answer, let me know. So if it is 450, let me know. If you got something else, you can press no, or if you need me to solve it, you can press no. All right. All right. Okay. Okay. So just if you think I did not get the answer. All right. 475. All right. Okay. Let's look at how to solve this. All right. Okay, so again, let's go with this. It's a 100 bus system. 90% sparsity, right? So number of elements would be, again, the assumption is that it is interconnected system. Number of elements would be 100 cross 100. It would be 10,000. Then you have to see number of non-zero elements. That would be zero point 0.1 into 10,000. That would be 1,000. Then number of non-zero of diagonal elements would be 1,000 minus 100, because there will be 100 diagonal elements. That would be 900, and therefore number of transmission lines would be 900 by 2 is 450. Is that clear, or is there some problem? Right. So did everybody else get make sense? So yeah, correct answer is 450. Okay. So Takura, Arun, sorry Varun, you guys, it's clear, right? Right. Okay. So there was a previous gate question like this, right? Right. So 450 is the correct answer. Okay, now let's start with the problem. The first question is for you to find y22. Can you calculate what y22 is? So you don't have to write the whole y bus matrix. You just have to remember what y22 represents, and just you can calculate it. This is like a 3-second problem. Answers? Okay, the first answer is minus. Okay. Okay, need more answers. Right. Okay. Are you guys writing the whole Bible? I'm going to solve this. Y22 is is equal to minus. So basically at node 2, it is basically the sum of all the admittances connected to node 2. There is minus J2 plus minus J5 plus J 0.05. So it will be J minus J 6.95. Do you get this answer? It is actually minus J 6.95. Basically, you are supposed to calculate Y22. So you look at what are the elements connected to node 2. There is this element, and this element. You take the sum of all the y's of the all the elements. So it is minus J2 plus minus J5 plus J 0.05. So this will be minus J 6.95. Did you guys get it? Alright. Okay, so next question, I want you to find the whole fibers. Find me the whole fibers. Okay, this will take I think 5 minutes. So it's 19 now, or 3 minutes or 4 minutes. Calculate the whole fibers. Okay. That I want you to figure it out. What do you think it is? Okay. Now that you have noticed it, let me know what is given. Impedance or admittance. So are the given values impedance or admittance? Takura Varun? Okay. So it's actually impedance. Because if you see the value corresponding to a reactor or inductance is positive. So it is actually, and the value corresponding to a capacitor is negative. If you go back to that table we made, you will find that that is for reactance, right? So sorry, for impedance. So when you are actually calculating the admittance, you have to take the inverse of this. So yeah, so it is basically what is given is what is given as impedance. Okay. So when you are done, just let me know. You guys are done. Good. So did you guys get this answer? Is this the answer you got? Okay. Dharani, what about you? I think she's off. So can't see my screen. What about others? Can you see my screen? Okay. Alright. Probably then you may want to refresh your connection. Or you also. Okay. So you got the answer? Okay. So I think except for one person, I think Mahak, you did not get it right. Uh, can you understand what was the mistake you made, or do you want me to explain this? You got it now, right? So you understood. See, when you're doing gate problems, it's not just about getting the right answer or the wrong answer. It's okay when you're practicing to get wrong answers, but it's always really important to understand what went wrong and where it went wrong. That means you are actually able to clarify what the assumption mistake you are making, right? So if you are getting a wrong answer, well and good. That means you are going to reiterate the concept, right? So see where you went wrong and what needs to be corrected. Right? Good. Right. Now let's look at a very Let's look at a very interesting thing. Stop sharing. All right. So I am giving you this Bible, right? So note down this Bible, right? Now can you draw the equivalent network for this? I hope you guys have noted it down. I want you to let me know when you are done. I want you to draw the network. Okay. So I'm just going to start drawing. And Dharani, are you guys having trouble figuring this out, or are you still in the process of drawing? Okay, everybody is done. Thank you. Right. Okay. So now let's see. Yeah. Are you able to see my screen? Yeah. Okay. So we are looking at a three bus system, right? So there is one. There is bus number one, bus number two, and bus number three. Right? That's one, two, and three. Right? So between one and two, there is a line. So and the value is J20. So the actual admittance is minus J20. Between 1 and 3, there is one line minus J10. And between 2 and 3, there is one line which is minus J5. So this one represents the admittance of line between 1 and 2 is between 1 and 3 is between 2 and 3. Right? Since it's symmetric, these values also are fine. Right? Now if you see an interesting thing over here, if you take the sum of the values over here, what do you get? This is 0. Right? You take the sum over here, it is 5. If you take the sum over here, you get minus 5. So basically it means that there is one more. So the diagonal element is made of this element plus this element plus one more element. If that element only shows up in the diagonal element, that means it's the shunt. So at bus number 2, there is a shunt of K5. At bus number 3, there is a shunt of minus K5. Okay, is this what you got? Okay, good. Well done, dear. So can you tell me what is the nature of the shunt connected at node number 3? Good. Node number 3 is inductor. Good. Node number 3 is actually 2, 5, 8, 4, inductor, and this is a capacitor. Right? Good. I hope that makes sense. Okay. Now that has happened. Uh, okay. Now try to answer this question. So this one we have answered as B. What is the answer for the first question? The impedance of transmission line between 1 and 2. Wait, I will give you the code. Okay. This is the old one. Pardon me. Yeah. Okay. Go for it. What is the answer? Sakura, Varun, I need an answer. Okay. Okay. Right. So the correct answer is B. So if you see, minus J20 is the admittance. What they have asked in the question is the impedance, right? So impedance is 1 by the admittance. So it is 1 by minus J20. It would be J 0.05, right? Does that make sense now? Okay, good. All right. This was one more question. This one we answered. You guys answered this correctly. This was shunt capacitance and shunt admittance. Right. Okay. 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 Now I want you to think about this and do this. So I haven't told you explicitly how this would work out, but again, this is like me. I'm throwing you into the middle of the sea with whatever I've told you right now. Tell me what would be the new fibers if the line between 1 and 2 is removed. How would it look like? So this is a fibers, right? So yeah, so when you guys are done with the new fibers, let me know. Okay, 1 done, 2 done. Okay, all of you are done. Good. So let's look at the answer. Right. So basically, when you are removing a line, right? If you're removing the line between one and two, right? So that would mean that y12 is equal to y21 is equal to 0, and it is connected between 1 and 2. So y11 new is equal to y11 old minus y12, and y22 new is equal to y22 old minus y21, right? So basically the fibers becomes a into minus 10, 0, 5, 0, minus 15, 10, I, and minus 15. Is that what you got? So thank you. That means all of you got the correct answer. Okay, so that means you got the correct answer. So basically, one advantage about with respect to uh, Vibers is that if you're adding or removing the line, you just need to update the corresponding Yij position and the Yii and Yjj, right? Okay, right. Now, right. Okay. Before we go on to the next topic, just wanted to let you know. So the question that you should have asked me is that, look, so we have the option of representing a network by either its impedance or admittance. Why do we choose to represent it by admittance, right? That is because as we saw, Vibus is extremely sparse, right? So just there are a lot of sparsity techniques in mathematics or matrix representation. So from a programming point of view, sparse bus is easy to compute with, easy to store. You need only very less amount of storage, right? So when we are doing load flow, right? When we are doing load flow or other system studies, it is easy to do that with a sparse matrix like this. So that is why we are actually studying how to form the Vibus, and we are representing the network by Vibus. Is that clear? And one more thing that I want you to notice is that the so from a practical point of view, when you're talking about an inductance, the J value would be high. It will be big. It will be, so if the value is like minus J5. From a practical point of view, the admittance of a inductive element will be high, and the admittance of a capacitive element will be very small. So these are the things that you will notice. That is because it is 1 by j omega c, right? This one would be xc. So it would, if you invert it, it would be, because it will be j omega c minus j omega c, and c is actually in the terms of microfarad. So this will be usually small. The admittance will be small, and here the admittance would be high. These are just a few things to remember. Let me see if I missed anything. Okay. Look, there is one more question that I want you guys to do before we proceed. This is a previous gate question, actually. Please, can let me just pull up that problem. Okay, sorry. Yeah. So are you able to see this question? So this is a gate question from 2012. Is it clear, or let me know if you want me to make it big? Yeah. So they have given the bus admittance matrix of a three-bus system, and it's saying that each bus is represented by equivalent pi network. So find the magnitude of the shunt susceptance connected between line 1 and 2. Okay. Once you are done, you let me know. If you are not able to solve the problem, let me know in the chat. All right, all right. So I have two answers. All right, let's look at how to solve this. Right? Deepak and Warren, do we need more time, or shall I start solving it? I'm going to start solving this, right? Let's look at this. So what they have given is the y bus. So if you take the sum of um, the row, what you get is the admittance. So if you take the sum of this thing, you will get as minus OGD plus J2, 15, okay, plus J2, and here also you will get plus J2, 20, 18, and 50, okay, here also plus J2. So basically they are saying that the shunt at bus 1 is J2, shunt at bus 2 is J2, and shunt at bus 3 is J2. Since there is line cut Y1 line, line between 1 and 2 and then between 1 and 3, that the shunt at 1 is basically y12 dash by 2 plus y13 dash by 2, right? Similarly, that is J2. Similarly, y shunt 2 is y12 dash by 2 plus y23 dash by 2 is J2, and ys3 is y23 dash by 2 plus y13 dash by 2 is J2. So now what they are asking is for y12. So we have three equations and three unknowns, and when we solve for it's a simple mathematical solution, right? When we solve it, you will get y12 dash as J2. So the answer is that clear? So people who got other answers, is it clear now? Right? All right. Okay. So far so good. Yeah, I just want to make sure that everybody is on the same page. Yeah, Varun, were you saying something? Okay, good. So yeah, so with that, I'm kind of stopping with the Vibus. All right. Now, okay, now let's look at construction of set bus. So far we were looking at the Vibus, right? So if we need the set bus, basically it is Vibus is, so set bus is Vibus inverse. But there is one problem, right? If you look at Vibus over here, let's look at the previous. Okay, let's take a fresh example. Okay, so then let's look at this example of a transmission line of a system. So we have a 3-bus system, and this is minus J10, minus J10, and minus J10. Right? So the Y bus would be J into minus 20, 10, and then 10 minus 20, 10, 10, 10, and minus 20. Right? Is that clear? Yeah, is that clear? Right, it's clear. Right. So the problem is that, so if we got the y bus as this, but if you try to invert this set as y inverse, what is going to happen is that you'll find that this matrix is not invertible. Plus, the determinant of this matrix will come as 0. So one way of identifying if this matrix is invertible is to take the sum of the rows. All sum of all rows would be 0. So you see this interesting correlation. Unless and until there is a physical connection between the network and the reference, this ground, that is, what is that? That will be the shunt, right? Unless and until there is a shunt in the system, you cannot invert the matrix to get the set bus. So there will be a lot of systems in the grid where there is no shunt element, and we cannot say, since we cannot invert the y bus, we don't have set bus, right? So in that case, what we do is that we form the set bus with a set bus building algorithm by taking one of the buses as reference. So when we are forming this y bus, the reference is actually ground, right? So what we do is that instead we will take one of the other buses as reference, and then we will build a network. So if there is no ground connection, if there is ground connection, even sometimes inverting a huge matrix will be difficult. So sometimes what happens is that matrix becomes so sparse that the matrix inversion becomes difficult. So we need a different approach to get the bus impedance matrix. Is that clear or is it confusing? So just because one person said clear, if it's not clear for you, you have to let me know. Okay? Thank you, Dani, for the feedback. But yeah, if it's not clear for you, please let me know. Okay. So now the question again comes. Now we have looked at Y bus. We were looking at why Y bus was advantages. Now why all of a sudden we are going to look at set bus, right? Why do we need to look at set bus? And the idea is that uh, set bus finds its application in fault analysis. So suppose there is a fault at this bus. What we do is that to find the fault current, we try to find the Thevenin's equivalent. I told you in the beginning that we will be having a lot of callback to network theory. So the fault current at that bus is usually calculated as VR1 and this set equivalent is usually Thevenin's equivalent, right? But when you're dealing with a huge network, trying to find the Thevenin's equivalent is not easy. So basically what we do is that we find the set bus and the set II will be the Thevenin's equivalent. It's actually a very beautiful concept. Once we actually look at how to build the set bus and we'll start looking at the problem, I'll try to tell you what is the physical interpretation of each element. So you should always ask the question that when we are writing a mathematical concept, it's just not about the mathematical jargon or it's just not about solving the problem. Each number that we write in the system actually has a physical meaning, right? It actually has a physical meaning. When we are writing the y bus over here, right, when we are writing the y bus over here, this 20 is not just a number that we put over here. It's not just a step in a mathematical approach. That 20 has a physical meaning. Can you tell me that what is the physical meaning of that minus 20? So what does the 20 mean? Minus 20 mean? Any idea? So basically I told you what Y22 is. So what does that mean? What does Y22 stand for? Or what is the physical significance of the minus 20? Okay. So the idea is it basically goes back to so basically for voltage applied, if voltage V is applied at node 2, then current I2 will be minus 20. The component of current due to V2 would be minus 20 times V2. That is the physical significance. It is basically that is the relationship, right? Is that clear? So always ask yourself the question, what does this mean, right? Right. Okay. So now let's look at how to build a bus impedance matrix, right? So basically, just let's summarize before we go forward that Y bus is used for load flow analysis and Z bus for short circuit analysis or fault analysis, right? So now we are going to build a Y bus, right? So what we do is that we take the grid, whatever grid network is given to us, and then we build it from scratch. So what we do is that first we decide the reference bus. So if we have a shunt, we always try to prefer to get ground as the reference bus, right? And then we take the first bus. So we take whatever is having shunt connection to the ground, and this value, right, this would be H01. So the first element, so the first set bus would be okay. So that is the first step. So any element that actually creates a new row and column in a set bus is called as a branch. So this is a branch. Okay. So if the add element creates a new bus to the existing system, then that element is called as branch. And when you are adding a branch, the size of the matrix actually increases. Before this, the size of the matrix was 0. Now when we added this element, we created one new node, 1, and then we set this also, the size increased by 1, right? Now what we are going to do is that we are going to add one more element over here. So basically the network diagram of any system would be given, but then we will have to deconstruct it in our mind and build the set bus like this, right? So set bus, now we have a new element. So the set bus would be Z01. Then what you do is that, so right now we are connected, this new element is getting connected to node number 1. So we will repeat whatever is there. And then for the new diagonal element, we will add whatever was there in the old diagonal plus Z1 to represent. This is also a branch because it created a new node in the system. So basically what we do is that we repeat the row and column of the node to which the new branch is getting connected, and then add the value of whatever is the value to the diagonal element. Is this clear? If it doesn't make sense, don't worry, we will, okay, let's add one more element, then it might make sense. Okay. Rather do this on 20 pieces. More drawing in 20 pieces. So basically, so far we have set 0, 1, 2, right? Set 0, 1, set 0, 2. Now, add one more element. Set 0, 3, right? Set 2, 3. So now the existing y set bus was set 0, 1, set 0, 1, 0, 1, 0, 1 plus set 1, 2. So this was the existing set bus. Okay, so this would be 1, 2, 1, 2. Now we are going to add a new element. This is the branch, right? So let's write the existing one, 0, 1, 0, 1, 0, 1, 0, 1, 2. So what we are going to do is that since we are adding the third element and we are adding it to node number 3, we are going to repeat row number 2 and column number 2. So what is column number 2? It is set 0, 1 and set 0, 1 plus set 1, 2, set 0, 1, set 0, 1 plus set 1, 2, and this is set 0, 1 plus set 1, 2 plus set 2, 3. Okay. Does that make sense? Is that clear? Does that make sense? Sakura, is it clear for you? No. Okay. So it's clear for everybody. Okay, then if it's clear for everybody, can you tell me what is the physical significance of any element in this one? What does it mean? Tell me what the physical significance is. If you want, you can unmute yourself and tell me, or you can type it in as well. If it is pretty long to type in, you can unmute and tell me. What is the meaning of said? What is the meaning of Z33? Anybody? Alright. I'll count to 3. 1, 2, 3. Alright. So the idea is that when you look at, suppose you're going to look at Thevenin's equivalent at node 3. But what does Thevenin's equivalent say? It is the impedance seen when you are looking from these 2 points, right? So when you look at these 2 points, this is basically ground, so these are connected. So if you look at this network, the Thevenin's equivalent impedance will be Z23 plus Z12 plus Z01. So Z33 is the Thevenin's equivalent when you look from this node. So if you look at if you look from this point, Z22, right? Z22 and ground. You trace this path, there is no connection, so it is open. Basically, it's Z12 plus Z01. So that's why Z22 is Z01 plus Z01. And if you look at any off-diagonal element, right? Okay, let's say 2, 3. What does it mean? What does Z23 mean? So Z23, what is Z23? Capital Z23. It is Z01 plus Z12. Right? To understand this, we probably will have to look at what is Z versus. Okay. What will be Z versus? It is V1, V2, etc. Vn, Z11, Z12, etc. Z1n, Zn1, Zn2, etc. Zn into I1, In. So basically, Z capital Z is suppose 1n means it is if there is for the current injection In at node n, how much the voltage at node I is affected. Basically, Zij means if I inject 1 ampere current or 1 per unit current at node J, voltage at node I will increase by Zi. Does that make sense? So basically, the physical significance of the diagonal element is that it is the Thevenin's equivalent at that point, and the physical significance of diagonal elements is that it actually shows the relative increase in voltage for current injection at a particular node. It basically tracks the effect of current injection at a node at a different node. Is that clear, Tarini and Varun? Right. Okay. So we'll just look at one more thing right now. Right. So now we looked at the condition where we are adding. So suppose now you are actually looking at a network like this. there is ground, bus is connected 1 and 2, right? So this is set 0 1 and set 0 2. So the set bus would be, you're basically adding set 0 1. Step 1 is adding set 0 1. Then actually the node to which the second element is connected is not 1. So instead of copying it here, you'll be copying the impedance of the node that is referenced. Make sense? Makes sense, right? Alright. So in cases like this, since there is no connection, so basically just think about this. So physical significance is that if I inject current at node 2, since there is no physical transmission line between 1 and 2, the voltage at 2 is not affected. So the voltage at node 1 is not affected. Same way, if a current is injected at node 1, the voltage at node 2 is not affected. And the Thevenin's equivalent, if you look at from node 2, will be only node 2, not node 1. So basically, this is actually an example of an islanded system. This is an island, this is an island, right? Is that clear? Right. So let's do something. Let's stop over here and we will resume with the set-bus building algorithm in the next class, right? So do you have any questions for the things that we have covered today? Okay, let's look at one question, right? Let's look at one numerical before we go. That would make more sense, right? So I want you to find the set-bus for this. Okay, consider all the impedances J point. To form the set-bus for the system. Just try that on your own. So let me know when you're done. Step is to add. Okay, so okay, good. So let me just show you how the solution will go. Right. So basically, if you look at it, I added the first element J0.2, so it is J0.2. Then I added element number 2, so it's what it is. So basically, if you look at it, first I'm going to add the first element. So it is going to be like this. Okay. So I just added the first element 0, 1, 8, 2. So then I'm going to add the next element. So the next element that I'm going to add is the it's going to create a new node, right? So it is going to be 0.2. I'm going to copy this row. I'm going to copy this column, right? And I'm going to add the value. So the 0.2 plus 0.2, that will be 0.4. So right now we have two nodes in the system, right? Now I'm going to add the third element, right? Third element would be so that would be just like the extension 0.2, 0.2, 0.2, 0.4. So we are connecting it to node number 2. So we are going to repeat this column 0.2, 0.4. We are going to repeat this row 0.2, 0.4. And we are going to add the new value that is 0.2 to this diagonal element. So 0.4 plus 0.2 is 0.6. So the last one that we are going to add is 4. But 4 is not connected to any other node. It is actually connected to the ground. So the idea is you write the existing matrix 0.2, 0.2, 0.2, 0.2, 0.4, 0.4, 0.2, 0.4, 0.6, 0, 0, 0, 0, 0, and 0.2. Is that clear? Yeah. Okay, set for 4 you did not understand. Okay. So up to set 3 you were able to understand, right? So This was the so this is the three things. So 0, 1, 2, 3. And the Z bus we got was 0.2, 0.2, 0.2, 0.2, 0.4, 0.4, 0.2, 0.4, 0.6. So now the new bus that we are going to add up here, maybe to avoid confusion, I will just read out in between. We have a post bus and that is directly connected to ground. Right? So what is the rule? We have to repeat the row and column of the node which is node to which it is connected. So 0.2, 0.2, 0.2, 0.2, 0.4, 0.4, 0.2, 0.4, 0.6. So which node is it connected to? Neither connected to 1, 2, and 3. So there is no dependency to 1, 2, and 3. It's actually connected to ground. So what we will say is that this is connected to ground and not to any other node. Right? If we are connecting this new branch, so we will this has to be 0, 0, 0, 0, 0. And since it's connected to ground, it will be 0 plus 1. Also think about it from a physical significance point of view. If you are taking the Thevenin's equivalent between node 4, there, there is no connection between this node to any other node. So the Thevenin's equivalent will be whatever is the shunt at node number 4. And for any current injected at 4, there is no physical connection between 1, 2, and 3. It is connected via ground, whose voltage is 0, right? There won't be any impact. That's why the off diagonal elements for that is 0. Is it clear now? Okay, right. I think I will stop here, right? Right. Okay. So we will continue where we stopped last class, which was bus admittance matrix, right? Okay. So we looked at a three bus system, which had three lines in between them, and we took KCL